want to see a dribble move? Watch this one. Double behind your back. Knock.
Areas where he can really use that skill. Curry, high off the glass for two.
Just highly skilled, Steph Curry.
Golden State.
Behind the back.
Stop and pop, and Curry with a rebound. That's why you want to keep Westbrook on the perimeter. Steph, again! The beautiful ball handling, and then the flip shot off glass. Steph lost the handle, regains. Goes around Westbrook again, down the lane, and lay it up and in.
When I met you in the summer, to my heartbeat sound, we found love as the leaves turn brown, and we could be together, babe, as the skies are blue. You act so innocent now, but you lied so soon.
Curry another three. That's two early threes for Stephen Curry. Could it be one of those nights? Tell him it's the Garden.
Shoots over Nash, knocked it down. Complete Human Torch mode. Curry steps back. Bang!
What a handle. First the crossover, then the step back, the balance, and nothing but the bottom.
Stephen Curry. Curry, three. Again, they're rolling from three. 5 of 6 triples for Golden State, and they lead by 15, 7 minutes into a closeout game.
He dribbled right to the spot, stopped, and it was gone.
And knocked it down. The 6th three-pointer of the night. Whoa! Curry with a focus move.
Well, I'd like to know who's the better ball handler.
Continued to play. That's inbounds. Curry. What a move! And then the jumper! Oh, man, the wizardry of Steph Curry on the handle, and then the hot hand. Oracle buzzing after that little foray. 3:06 remaining in the first. Between the legs, spin around, crossover, and have the sweetest jumper in the league. The Warrior lead.
But he got the ball on the move. Oh, my goodness. Oh, my goodness. Oh, I'm sorry, George. Oh, my goodness. Oh, that's a shake him up there. Oh, no, can I have some fries with that shake? Oh, my goodness.
Curry, all pretty fake, pulls up. There's the first field goal. That was sweet.
What a move. I mean, what do you do defensively? The league right now, I think, is between Steph Curry and Kyrie Irving. The ability to dribble the basketball in traffic.
Curry splits the defense behind the back. Fires a three. Oh, he puts it in. What a spectacular move. And it's the largest lead of the game.
That could be the greatest move I've ever seen. No, I'm being serious.
I love looking at Steve Kerr's reaction after that move. I mean, you're shocked as a coach, as a fan, as a teammate, as a player going in.
Yo, Dre dropped the verse. It's going down, fade to Black Street. The homies got at me, collab creations.
Alright, Orcas, this is day 2 of learning about atoms. I'm going to see, I hope you remember what we learned yesterday about atoms being the building blocks of everything, building blocks of matter, and everything we see, taste, touch, and smell around us are made of atoms. We also learned that even though atoms means undividable, or unable to be divided, we learned that there are things smaller than an atom, such as a proton, which is positively charged, neutrons, which are neutrally charged, and electrons, which are negatively charged. So we're going to roll on, guys. Now, before we do that, we're going to review a little bit of levels of organization from ecology. So let's see what you know.
East side to the west side, pushing fat rides, it's no surprise. She got tricks in the stash, stacking up the cash, fast when it comes to the gas. By no means average, it's on when she's got to have it. Baby, you're a perfect 10, I wanna get in, can I get down so I can win? I like the way you work it, no diggity, I got to bag it up. Bag it up. I like the way you work it, no diggity, I got to bag it up. Bag it up, girl. I like the way you work it, no diggity, I got to bag it up. Bag it up. I like the way you work it, no diggity, I got to bag it up. She's got class and style, street knowledge by the pound. Baby, never act wild, very low key on the profile. Catching feelings is a no, let me tell you how it goes. Herbs the word, spins the verb, lovers hit curves so freak what you heard. Rolling with the fatness, you don't even know what the half is. You got to pay to play, just for shorty bang bang to look your way. I like the way you work it, trump tight all day, every day. You're blowing my mind, maybe in time, baby, I can get you in my ride. I like the way you work it, no diggity, I got to bag it up. Bag it up. I like the way you work it, no diggity, I got to bag it up. I like the way you work it, no diggity, I got to bag it up. Bag it up, babe. I like the way you work it, no diggity, I got to bag it up. Hey yo, hey yo, hey yo, hey yo. Hey yo, that girl looks good. Hey yo, hey yo, hey yo, hey yo. Play on, play on, play on. Hey yo, hey yo, hey yo, hey yo. You're my kind of girl. Hey yo, hey yo, hey yo, hey yo. Hey yo.
'Cause that's my peeps and we rose deep, flying first class from New York City to Black Street. What you know about me? Now don't thing. Cartier wooded frame sported by my shorty. As for me, icy gleaming pinky diamond ring. We bees the baddest click up on this scene. Ain't you getting bored with these fake broads? How shows improves, no doubt. I been you so. Please excuse if I come across rude. That's just me, and that's how a player's got to be. Stay kicking game with a capital G. Ask the peoples on my block, I'm as real as can be. Word is born. Faking moves never been my thing. So Teddy, pass the word to your nigga Chauncey. I'll be sending a call, let's say around 3:30. Queen Pen and Black Shoes.
I like the way you work it, no diggity, I got to bag it up. I like the way you work it, no diggity, I got to bag it up. I like the way you work it, no diggity, I got to bag it up. I like the way you work it, no diggity, I got to bag it up. Yeah, come on. Becky in full effect, Lisa in full effect, Pinky in
After these messages, we'll be right back.
The power of the atom, greatest source of energy man has ever discovered, is now serving in many ways, from atomic submarines and ships to nuclear fuel generation of electric power. Planning ahead for California's growing electric needs, PG&E, in partnership with General Electric, has had Vallecito's atomic power plant in operation since the fall of '57. Its license from the Atomic Energy Commission was the very first one issued. Now we're building a much larger atomic electric plant to begin operation in 1962 at Humboldt Bay near Eureka. Today, atomic electricity costs more than conventional power in the United States, but at PG&E's Eureka plant, engineers expect to break this cost barrier and become the first in America to achieve economic atomic electricity. Creative engineering, research, and pioneering development like this help keep your PG&E service your best bargain.
Relax as you look at this next image. But don't look away until I tell you to. Got it? Keep looking. Keep looking. Now, quick, look at your hand. Is it spiraling?
The brand new season, Brain Games, 7:30 Sundays on National Geographic Channel.
Some people live for the fortune. Some people live just for the fame.
What makes one substance different from another? What makes the glass in these goblets different from the diamond in this ring? They are both clear, sparkling solids, but diamonds are one of the hardest materials on Earth and are even used to make saws which can cut rock. And glass is fragile, easily broken. The difference lies in the types of atoms that make them up. What makes atoms different from each other? We are going to take a look inside atoms and examine their atomic structure. Atomic structure refers to the arrangement and number of smaller particles of an atom. These smaller particles that make up atoms or subatomic particles include protons, neutrons, and electrons. Let us consider each subatomic particle separately. This is an atom of carbon, a substance found in charcoal and diamonds. The nucleus is the center or core of the atom. It is where 99.9% of an atom's weight is located. The nucleus contains protons, as seen here in red, and neutrons, seen here in green. Protons are positively charged particles, symbolized here by a plus sign. All protons are the same, no matter what type of atom they are in. The weight of subatomic particles is measured in units called atomic mass units. A proton weighs 1 atomic mass unit. There are millions and millions of protons in a single drop of water. The other subatomic particles located in the nucleus are neutrons. A neutron is a neutrally charged particle. They do not have a charge. Neutrons also have an atomic mass of about 1 atomic mass unit. While the nucleus contains most of the mass of an atom, it takes up only 1/100,000th of an atom's space, equivalent in ratio to this ball in this meadow. While all atoms have a nucleus, what is it that makes them different? The answer lies in their number of protons. The atomic number is the number of protons in an atom. For example, the element carbon, which is what makes up the graphite in this pencil, has an atomic number of 6. It has 6 protons. All atoms of carbon have the same atomic number of 6. The atomic number also equals the number of electrons. Therefore, carbon also has 6 electrons, seen here in red. Copper, a different element, has an atomic number of 20. It is useful to know the combined number of protons and neutrons in an atom. The atomic mass, also known as the atomic weight or mass number, is the sum weight of the protons and neutrons in an atom. Let's take the element silicon, symbolized by the letters Si. Silicon is a major element that makes up the sand on this beach. Silicon has 14 protons and 14 neutrons that add up to an atomic weight of 28 atomic mass units. While most types of carbon, such as that in these trees, have 6 protons, the number of neutrons may vary. Isotopes are atoms of the same element with different numbers of neutrons. For example, carbon can have an atomic mass of 12 or 14. Carbon, with an atomic mass of 12, seen here with 6 red protons and 6 blue neutrons, is referred to as carbon-12. But carbon can also have an atomic mass of 14, called carbon-14, seen here with 6 red protons and 8 blue neutrons. Carbon-14 in nature is unstable and gradually deteriorates. With specialized equipment, scientists can estimate the age of objects, such as this bone, by measuring the degradation of carbon-14. Because most elements have more than one isotope, each element has an average atomic mass, calculated from the average mass of its isotopes. The fast-moving particles around the nucleus are electrons. Electrons are negatively charged particles. They are a fraction of the size of protons or neutrons. To help you visualize this size difference, if this ball were a neutron, then this P would be an electron. An electron weighs just 0.0006 atomic mass units. Because electrons weigh so little, their weight is not even considered in calculating an atom's atomic mass. The electrons move very quickly, perhaps as quickly as 1 billion times a second around the nucleus, forming what is called an electron cloud. The electron cloud is the space in which the extremely fast-moving electrons are likely to be found. As scientists learned more about elements and atoms, they developed a way to organize them in a logical manner. They created a chart to organize elements by their atomic structure that is referred to as the modern periodic table. The modern periodic table represents a remarkable scientific endeavor. It takes thousands of seemingly unrelated pieces of information and fits them together in a logical format. This organization is dictated by the periodic law, which states that both chemical and physical properties of elements are periodic functions of their atomic numbers. The position of elements on the periodic table is dictated by the number of protons, or their atomic number. Notice how the top number, the atomic number, increases from left to right. The elements on the periodic table are represented by their chemical symbols. A chemical symbol is an abbreviated way of symbolizing an element with 1 or 2 letters. For example, the element oxygen, found in the air we breathe, is symbolized by the letter O on the periodic table. Oxygen, along with hydrogen, is a fuel commonly used in rockets. Hydrogen is symbolized by the letter H, found in the upper left portion of the chart. Let's take a look at another element, calcium. Calcium is an element found in the human body and in the bones of other animals. Calcium is also common in rocks, such as limestone and marble seen here. It is located here on the periodic table. The chemical symbol for calcium is Ca. On top of the chemical symbol is the atomic number. The atomic number of calcium is 20. Remember that the atomic number is equal to the number of protons. Here you can see 20 protons with a positive charge in the nucleus. Below the chemical symbol for calcium is the atomic mass. Here you can see that the atomic mass of calcium is 40.08 atomic mass units. You will notice that the periodic table is organized in a grid with rows and columns. There are 18 columns called groups or families. These groups or families have elements that possess many similar chemical and physical characteristics that we will explore later. The rows in the periodic table are called periods. Unlike the elements in families, the elements in periods do not have a great deal in common. But by looking at elements across the periods, we notice some interesting patterns. There are 7 periods or rows. Notice that a portion of rows 6 and 7 has been removed. These periods are still part of the periodic table, but have been moved to make the table shorter and easier to read. As you go from left to right in the periodic table, one obvious trait stands out. The atomic numbers increase in regular intervals. For example, you see how the atomic number increases starting with silicon with an atomic number of 14, then phosphorus with an atomic number of 15, then sulfur with an atomic number of 16, and so on. Of the 109 known elements, the vast majority are metals. These are highlighted on the periodic table in green. While you may think of objects such as silverware, pans, and wires as metals, other elements such as calcium and sodium are also metals. Elements toward the middle and left, such as mercury, are also metals having metal-like properties, such as shininess as seen in this aluminum foil, and are malleable, the ability to be shaped. Metals are also good conductors of electricity, such as that found in this electric fence. Generally speaking, metals also have a high density, as is the case with this piece of rapidly sinking lead. Magnesium, a metal commonly used to make airplanes, is in a specific family of metals called the alkaline earth metals, highlighted here in blue on the periodic table. The alkaline earth metals are a highly reactive group. For example, magnesium, seen here, brightly reacts when burned. Within the metals are the transition metals, seen here in green. They are less reactive than the first two groups of metals. There are many commonly used metals in the transition metals, including iron, used in making machinery and bridges, copper, used in wires and pipes, and tungsten, used in light bulbs. These shiny metals tend to be good conductors of electricity. Transition metals, such as iron, zinc, and cobalt, are also used to make colorful paints. The elements to the right of the staircase-like line in the periodic table are called the nonmetals. The nonmetals tend to have opposite properties from the metals. These elements tend to have a dull luster and are brittle, such as this sulfur. They have low densities and melt at lower temperatures. They do not conduct electricity well. One such family of nonmetals are the noble gases, highlighted here in light red. These elements are found in small amounts as gases in the Earth's atmosphere. Argon is the most common of the noble gases and makes up about 1% of the Earth's atmosphere. Many signs are made with inert gases, such as this neon-filled sign. The elements highlighted in orange, just to the right and left of the staircase line, are called metalloids because they have properties of both metals and nonmetals. Metalloids are solids that conduct heat and electricity better than nonmetals, but not as well as metals. Silicon is one such metalloid that is used in computers. It is valued in computers because it is a semiconductor, meaning it is somewhere between a conductor and an insulator of electricity. We have explored just a small amount of the information found on the periodic table. Next time you get a chance, spend some time exploring the periodic table. You will be surprised at the amount of interesting facts you will learn. Fill in the correct word when you hear this tone. Good luck, and let's get started. Number 1. Atomic refers to the arrangement and number of smaller particles in an atom. Number 2. The is the center or core of an atom. Number 3. Are positively charged particles located in the nucleus. Number 4. Neutrons have a charge. Number 5. Are atoms of the same element with different numbers of neutrons. Number 6. Are subatomic particles with a negative charge. Number 7. The sum weight of protons and neutrons in an atom is its atomic. Number 8. Elements in the periodic table are ordered according to their atomic. Number 9. Are the most common elements on the periodic table. Number 10. Elements in the family called the alkaline earth metals are very.
Some people live just to play the game. Some people think that the physical things define what's within. And I've been there before, but that life's a bore. So full of the superficial. And some people want it all, but I don't want nothing at all. If it ain't you, baby, if I ain't got it, you, baby. Some people want diamond rings, some just want everything, but everything means nothing if I ain't got you. Some people search for a fountain. The promise is forever young. You know, some people need 3 dozen roses, and that's the only way to prove you love them. Hand me the world on a silver platter. And what good would it be with no one to share, with no one who truly cares for baby. Ooh, said nothing in this whole wide world don't mean a thing if I ain't got you with me, baby.
It's a beautiful night. We're looking for something dumb to do. Hey, baby, I think I wanna marry you. Is it the look in your eyes, or is it this dancing juice? Who cares, baby? I think I wanna marry you. Well, I know this little chapel on the boulevard we can go. No one will know. Oh, come on, girl. Who cares if we're trash? Got a pocket full of cash we can blow. Shots of Patrol, and it's on, girl. Don't say no, 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 no. Just say yeah, 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 yeah. And we'll go, 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 go. If you're ready, like I'm ready. 'Cause it's a beautiful night. We're looking for something dumb to do. Hey, baby, I think I wanna marry you. Is it the look in your eyes, or is it this dancing juice? Who cares, baby? I think I wanna marry you. Oh, I'll go get a ring, let the choir bells sing like ooh. So what you wanna do? Let's just run, girl. If we wake up and you wanna break up, that's cool. No, I won't blame you. It was fun, girl. Don't say no, 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 no. Just say yeah, 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 yeah. And we'll go, 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 go. If you're ready, like I'm ready. 'Cause it's a beautiful night. We're looking for something dumb to do. Hey, baby, I think I wanna marry you. Is it the look in your eyes, or is it this dancing juice? Who cares, baby? I think I wanna marry you. Just say I do. Tell me right now, baby. Tell me right now, baby. Baby, just say I do. Tell me right now, baby. Tell me right now, baby. Baby, oh, it's a beautiful night. We're looking for something dumb to do. Hey, baby, I think I wanna marry.
After these messages, we'll be right back. Yeah.
Adelante.
Permiso, don César.
¿Cómo está? ¿Cómo le va?
¿Cómo está?
¿Me permite sus documentos, por favor?
Sí, aquí. El currículum.
Bien. Ingeniero comercial.
Así es.
Perfecto. ¿Licencia a conducir la tiene al día?
Sí, al día.
Ya, perfecto. ¿Usted está más o menos claro cuáles son los propósitos de nuestra empresa? ¿No hay problema?
Bueno, principalmente...
¿Tuvo algún problema al llegar acá ahora?
No.
Porque estamos un poquito...
A
Madre. Perfecto. Aquí están sus...
Cuidado.
¿Sí? Ah,
Sí,
perfecto.
Mire. Mire. ¡Cuidado, no!
¿Hay alguien? ¡Don César!
¡Aló!
Watch the image on your screen closely. We've got a quick question for you about these two squares. True or false? This top one here is a darker gray than the bottom one. Pretty obvious, right? Well, maybe not, because the answer is actually false. Believe it or not, they are exactly the same color. Still don't believe these two squares are the same shade of gray? This man, experimental neuroscientist Bo Lotto, is going to show you why your brain is constantly being fooled by what it sees. We'll take a look at the illusion again. If you want, try holding up one of your hands and block this section of the image. If you're having trouble seeing it, we'll help you out. Crazy, right? Take a look at this object. One glance and you know what it is. But how do you know what it is and where it's positioned in space? Well, let's break it down. The light reflected by this object is converted by your eyes into an electrical signal and is sent down a neurological pathway called the optic nerve to the back of your brain. Starting in this region, called the visual cortex, the image is cross-referenced with memory of past experiences stored throughout your brain as you try to identify the object. Once it's figured out what it is, your brain has to decide how the object is positioned in space, and one of its most reliable tools is to use shadows. Here's another illusion to show you how that works. Take a look at that basketball again. We're going to put it on the court and move it along a diagonal. Now we're going to add a shadow. It's still moving in the same way, right? Okay, so what if we change the position of the shadow? Do you think we can trick your brain into seeing the ball's motion differently? Does it look like the ball is taking off now? Let's tweak the shadow one more time. What's the ball doing now? Looks like it's bouncing, right? In a world with a single light source, your brain has learned to trust shadows as a near foolproof way to know the behavior of objects in space. And in general, it's worked. Until now.
Behind me, there are two shadows that both appear gray because we have two white lights that are facing me. Now, if we replace with a purple filter, let's see what happens to the colors you see. The shadow no longer looks gray, it looks green. So the question is, where is that green light coming from? Well, there is no green light. The shadow's gray, but it looks green. Why? Because of the color that's surrounding it. Context is everything.
Let's start with this illusion. Stare at the X in the middle of the image. Do you see the green dot moving around in a circle? Now try to follow that green dot with your eyes. Nothing there, right? This illusion helps demonstrate how quickly your brain finds motion in your surroundings. Want to see how it does this? As you watch the X, neurons throughout your visual cortex compare the image you're looking at from one moment to the next. Specific neurons track the changing position of objects between the images, allowing you to comprehend them as moving through space. In the moving circle test, the missing dot here leaves an after image. As this after image shifts position, your brain sees a pattern that it decides is motion, and it stitches together the frames to see a moving green dot. Cool, right?
Is it the look in your eyes, or is it this dancing juice? Who cares, baby? I think I wanna marry you.